Hi, this is Stephen Brower from Mountain Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. This video is meant to accompany, well, there's, I guess, 3 documents that are attached to Canvas, which step through a 3-variable and 4-variable examples. So of the 3 links that are there, the 2 that are the demos, this is really accompanying the demos. So if you haven't peeked at it yet, what you might want to do is peek at the introductory document first before. Let's make sure I can get this right. Whoop. And I'm referring to this first document right here. So the Chapter 11 supplement, the Karnaugh Map, that might be a one thing to peek at before, at least peek at it, but before continuing on with this video. Okay, so here I'm just going to take through 2 of the examples. And so the premise behind this, a Karnaugh Map, it's a method that's used to simplify a Boolean expression. There are other ways to simplify Boolean expressions. So the Stallings book, Chapter 11, does give the postulates, the theorems, etc., and that those things can be applied to a Boolean expression to figure out how to simplify it. And maybe some, or even can look at the Boolean function that's here and see the simplification before I go any further. But what I want us to do, in computer science, there are a number of algorithms that you have to demonstrate that you can trace that algorithm and show the logic that's being done. And so sometimes initially, some of the simple examples that we'll start with will be almost in a sense too simple, but it's just trying to illustrate the process that I do want you guys later. So there is going to be a lab this week where you're going to have to do a Karnaugh Map. That's not going to be as obvious as the examples I'm about to do here. And possibly on an exam, I may ask you to simplify a Boolean expression and using a Karnaugh Map, and you'll have to go and apply that knowledge to it. So what I'm getting at is you're looking at it and you say, well, it's obvious why we're doing it. It's obvious why we're doing it. For the ones that aren't obvious, that's why we're doing it. Okay, so what I have, this top part right here, this is the logic table. I haven't yet filled it in, but for this expression, of which it's A equals F and parentheses E or F or G. Since this is accompanying the Stallings book, that's why I'm using the Stallings format for this expression, and I'm using the 0s and 1s as the inputs for the F and the G. Now, one thing that we can do in terms of the short circuiting is when we realize that this is F and the expression, anywhere F is false, the expression as a whole is going to evaluate false. So for the ones where F is false, I can just go and put in the those values. So then what we have is inside, we have E or F or G. Well, E in this case, those are true. Well, it takes care of those. And so here it's E or F. Well, the F is here. And by the way, you may already have figured out what this is going to be. But again, we're just going through the process. So this is just the logic table for the inputs, the Boolean variables of E, F, and G as inputs to this function. And this would be the output of those functions given these inputs. And now the Karnaugh Map part, that's this piece down here. The idea in the Karnaugh Map, it's that the elements that are here are the same as the elements that would be here. They're just arranged differently. What Karnaugh has done is he uses topology as a way of looking for patterns for simplifying the expression. And so one thing with filling out the Karnaugh Map is we would use, well, in the case of 3 variables, 1 variable on one side, 2 on the other. As we'll see in the next example, I just want to jump ahead, 2 variables on one side, 2 variables on the other. And then what we have to represent are what are the possibilities for that variable. So with an E, well, the 0 and the 1, well, this would represent not E, this would represent E. If the two variables over here are F and G, then this would represent not F, not G, not F, G, F, G, F, not G. So that's what those 1s and 0s would represent over here. When we go row to row, we only want to change one bit. Well, since we only have one bit, there only is one change. But when we go column to column, we have to only change one bit, and so the order might look different than what you might expect. But between this column and this column, the only bit that's different is the second one. Between this column and this column, the only bit that's different is the first one. Between this column and this column, the only bit that's different is the second column. And if we do a wrap, this lastmost column to the firstmost column, the only bit that's different is the first. And that's the thing is with the Karnaugh map, we actually can do wrapping around the edges. Again, this comes into topology, and well, it comes into topology. So once the table is laid out, then it's a matter of saying, okay, looking at these inputs, what are the values from the table? Well, when E is false, F is false, and G is false, E is false, F is false, and G is false, the expression is 0, so this is 0. So here we have here, E is false, F is false, G is true, E is false, F is false, G is true. The result is 0. Oh, 0, wrong key. Here, E is false, F is true, and G is true. Well, we have to come to this row. E is false, F is true, G is true. It's a 1. And then this last one, E is false, F is true, G is false. That's this row right here. The result is 1. Okay. So now the next row in the Karnaugh map, it's E is true, F is false, and G is false. That's this one here, comes here. And then this one, E is true, F is false, and G is true. That's this one right here. Now this one, E is true, F and G are both true. That's this row here. That's the value 1. And then the last one here, E is true, F is true, G is false. That's this row right here, and we have the 1. Okay. Now, what's done next in the Karnaugh map is we have to do groupings in terms of powers of 2. So like the largest power of 2 that we can do a grouping for. And so what I'll try to do is sort of like as a rectangle, I'll have to then go and shade it. But this right here, that 4, that's a power of 2. This seems to be the largest grouping of 1s that we can have. And what we're looking for is we're looking for contiguous 1s. And in this case, we have this right here. This is our mapping in terms of our 1s. Now let me just go and, have no fill on this. And just so it stands out, let's just then get, we see that is the mapping. Okay, so now we kind of want to look at to see what variables have everything represented. Well, wait a minute, if we look at the rows, we have E. Since there's both rows, that means E is both false and true. So E is not going to be in our final formula. When we look at the columns, the second bit here, the second bit, which is the G, we have a 1 here, and we have a 0 here. So both possibilities for G are covered by this mapping. So what's left is the leftmost thing, which is 1, which means true, which means F. That would mean that the reduced function is A equals F. What? That is the reduced function. So by doing this mapping, we were able to come up with what the reduced formula is. Again, this table here is built from the logic table. And by the way, in theory, we actually could have started with just the Karnaugh map and filled in. We got to make sure when we build the map that column to column, only 1 bit changes. Row to row, only 1 bit changes. And then what we do is we want to group the largest power of 2, and then we look at what is covered. So E, both true and false, are represented by these rows. And then in terms of the columns, G has both true and false, but F is only true. And so the resulting formula is A is F. And so if we compare our F to our, to our final, we see that they match. And so that given all these inputs, it's whatever F is producing the same thing. So that is the simplified version of this. Okay, I'm looking at the clock. It's 10 minutes. What I'm going to do is I'm going to make this part 1 of the Karnaugh, and then in part 2, I will then tackle this next one, which has 16 inputs and a 4x4 table. So look for part 2.